Students, we have discussed in the last class about the Saline solutions, and especially I have discussed about the regular solutions. Now, in this lecture, as I am going to discuss about order solutions, so it is better that we start with a simple atomic scale picture of Saline solutions. As you know, Saline solutions actually can be of two types. Basically what we call as a substitutional Saline solutions and interstitial Saline solutions. Substitutional Saline solution means we can replace the atoms of a lattice or sitting in a crystal structure by some other atoms. Like here in the first case, the green atoms are actually solvent atoms, just like in a solution in liquid, and the blue atoms are known as solvent atoms. So, that means initially all the atoms are occupied by the green, and later on some of the atoms of blue type have replaced the green atoms. So, here actually you see there are 5 green atoms in the 2-dimensional lattice, and remaining are the blue 5 blue atoms remaining are the green atoms. So, question is this direct replacement of atoms is known as substitutional Saline solutions. That means we are substituting the atoms of one type by other. We can also have a situation in which we do not need to replace the atoms sitting at the lattice positions, but we can actually accommodate solute atoms at the interstitial positions. That is shown here, the blue ones actually small size solute atoms, they are sitting at the interstitial positions. Here you can see there are several ones are shown. So, this kind of Saline solutions are very widely seen, like steel, in which carbon is actually added to the iron, goes into the interstitial positions. So, that is normally the picture of Saline solutions. You can have only two types. Now, we can actually vary their level of complicacies, and that is what we are going to discuss. To show you a 3-dimensional crystal structure and how atoms are arranged, this is a Saline solutions of known as brass. Brass consists of copper and zinc, and it can have different concentrations of zinc in copper. But you see here the zinc atoms which are actually grey, they have replaced some of these copper atoms which are showing as a yellow. Similarly, on the right side I am showing a BCC structure of iron, and carbon atoms are shown as a dark atom small size, they are sitting in the interstitial positions. So, anyway whether it is a 2D or 3D, this is what actually observed in the Saline solutions. Saline solutions are the phases which we will see more in phase transformations, because we will see when you study about the solid state phase transformations how the Saline solution phases will be transformed into some other things. It will be clear to you then how these concepts are important. Now, as I told you, Saline solutions can be different types. The random ones, that is what we discussed in the regular solution model, are shown on the left picture. That is why the black atoms which are known as solute here sitting randomly in the, or rather replace the white atoms randomly. That is why they are called random Saline solutions. We can also have order Saline solutions. That means the black atoms are now sitting at exact positions in the lattice. Okay, you see here they are regularly sitting at different defined positions. Similarly for the white atoms. Okay. So, that is basically substitutional random and substitutional order type. Now, we can also have interstitial order. What is the meaning of interstitial order? That means when the interstitial atoms can actually sit specifically specific positions or specific interstitial positions in the lattice. That is what is shown here. The black positions are actually interstitial positions where the atoms are sitting, but they are sitting only at fixed positions, they are not randomly sitting in the lattice. That is why it is called interstitial order Saline solutions. There are many actually, we will see some examples later, but there are many such solutions exist in the literature. Similarly, you can also have clusters in the substitutional Saline solution. Cluster means instead of black atoms which are solute sitting randomly in the lattice or in a defined positions in the lattice, they can be clustered around certain positions. Like you can see here, this is where it is clustered, this is where also there are several places the atoms are actually clustered around. Cluster means they are sitting together, they are not widely dispersed in the lattice positions. So that means substitutional solutions can be of 3 types: random, cluster type or order type. Now depending on their nature, the free energy curves will change. In fact, some of these I will discuss in the lecture today to give you a better idea of what is a kind of order disorder, because ordering is very important for us. See, this is a BCC unit cell. Okay, why it is a BCC unit cell? Because all the atoms are actually similar type sitting at the corners of the cube and the center of the cube. There is no difference of type of atom sitting at these positions. On the other hand, the moment I put a specific, suppose pink color atoms in the body center positions, whereas the corners of the cubes are occupied by the green atoms, then it is called B2 structure. The reason being is that we can have actually 2 different lattices here. One lattice, so which is simple cubic, occupied by only the green atoms, other lattice which is also a simple cubic type, in which these pink color atoms will be occupied. So that means we can actually talk about 2 different lattices in the B2 structures. On the other hand, in the BC structure it is a simple lattice, that is the body center cubic, because we do not differentiate type of atoms sitting at the corners or at the body center. But here we are specifically allowing green atoms sitting at the corner positions and the pink atoms sitting at the center positions. So this is known as beta bus, like I discussed, or this is known as beta prime bus, because this is order. So this is the first type of ordering we actually normally observe. BCC transforming into B2 is the order disorder transformations. Okay. Now how this will happen and what are the thermodynamics and all this we will discuss later part, but to make you clear that this is an phase transformations by the way. Now we can complicate more, but they are not complicated structures. Okay, let us look at silver copper. Silver copper is a classic order disorder phase transformation system. Copper atoms, if I allow them, this is a phase center cubic structure. Suppose if atoms are randomly sitting in the phase center cubic structure like copper and silver, there is no specific type of atom sitting at the different positions, then we call it FCC. But the moment copper atoms are only sitting at the 4 FCC positions and corner as well as 2 FCC positions, then it is called as order structure. Here if you look at carefully, there are 1, 2, 3, 4 copper atoms in the unit cell, but each copper atom is shared by 2 unit cells, because they are sitting at the phase center position. So there are actually 2 copper atoms per unit cell effectively. On the other hand, there are one gold atom coming from the corners, because corners are shared by the 8 cubes, and one coming from the phase center positions. So there are 1 or 2, so therefore 1 plus 1 is 2. So that means there are 2 gold atoms and 2 copper atoms. So that means this is a CuAu structure. This is known as L21 structure, okay, because atoms are actually occupying specifically 4 phase center positions by the copper and corner atom plus 2 phase center positions by the gold. We can change the situation completely other way. How? Suppose if I put corner atoms as a copper and all the phase center positions atom as a gold, then I will have what is known as Au3Cu structure. Very clear, there are 6 gold atoms in the lattice, and as you know, each gold atom is shared by 2 unit cells. There are actually 3 gold atoms, but there are only 1 copper atom effectively in unit cell, because these corners are shared by the 8 cubes. So that is why it is called Au3Cu structure. This is actually known as L12 structure, order structure. Okay. So you can clearly see, by simply form a disorder structure, we can build in order structures in a variety way. One is a B2, then this L12, L21, different kind of structures can be created. Okay, now there is another example I like to give, which is the classical example known as Ni3L. This is also known as L12 structure. simple FCC unit cell, but this is no longer a FCC unit cell because atoms are specifically occupying different positions. As you see here, aluminum atoms are sitting at the corners, that means there are 1 aluminum atoms coming from the effectively coming from the unit cells, but there are 3 nickel atoms effectively coming from the unit cell because nickel atoms are occupying the first center positions. Now this has 4 sublattices specifically. 1 sublattice is because of aluminum and 3 sublattices of nickel. Why 3 sublattices? Because we can actually put 2 atoms, 2 face center atoms here like this and generate 1 sublattice. Similarly, we can actually have another 2 like this, I think, yeah, another 2 like that, another 2 like this. So by drawing a whole many unit cells, we can actually generate these sublattices. So basically speaking, they are all lower order structures, or that means crystallographically, and that is why they actually order atomically. So by giving these examples, it is evident to you that order structures basically come from simply putting the atoms in the specific positions in the unit cell. Similar thing, if I actually have a FCC unit cells like this, if I draw it here and put a random arrangement of the nickel and aluminum atoms, then what will happen? It will be simply FCC unit cell. If I do not demarcate between the type of atoms sitting at the corners and the face centers, then it becomes a FCC structure. So FCC becomes L12 when nickel atoms start sitting at the face center position specifically, and this is known as order disorder transitions, and this is basically very important order disorder transitions because this is used, this material is used directly in the application like turbine engines or even in the jet engines. Okay, now giving this idea about order substitutional order structures, let me just tell you that how the interstitial solutions form. Normally interstitial solutions form by occupying the voids in the lattice. So suppose this is a BCC unit cell, let us suppose this is a BCC of iron. There are actually both octahedral and tetrahedral voids. Octahedral void is shown here, you can see. Similarly, in a FCC unit cell like this, octahedral void is shown there. So if I put a carbon atom there, then carbon atoms can occupy in each of these faces. They will be called the sitting at the octahedral voids. Similarly, there are many many octahedral voids present in FCC structures. So FCC is like a gamma iron, solutions of the FCC iron in and carbon. So here I am showing you all the in the FCC structure all the octahedral void positions. You see here there is one at the center, then there are sitting at the edges. So there are many such. Similarly, I am showing you here the tetrahedral positions in the FCC unit cells. There are actually many. Actually, you can see 1, 2, 3, 4, 5, 6, 7, 8 tetrahedral voids present there. So there are empty number of voids present in the unit cells which can be filled up with this smaller size these interstitial atoms, and they can form different solutions. You can have carbon, sulfur, nitrogen, oxygen, any kinds of things possible. So to give you an idea about the oxygen, suppose this is a hexagonal crystal structure of aluminum oxide. You see here the oxygen atom goes into the hexagonal structures. Okay, hexagonal means these grey color atoms are oxygen sitting at the hexagonal lattice positions, and aluminum, because smaller atoms, they actually go into the octahedral positions here, and these are the octahedral positions of aluminum, and that is why it become Al2O3 Al2O3 structure. Okay. So this is gamma aluminum oxide, by the way. Aluminum oxides are different crystal structures, but we can actually form this way different kinds of solutions, whether it is a metal or ceramic, it can be any types. Now upon giving you this idea, so let me just go back and tell you, so how do we deal with the free energy composition diagrams of these structures, okay, order structures. As you have seen, the most of these order structures, now I will go to the board and discuss, most of the order structures actually are stoichiometric compounds, like I told you about Ni3Al. It has a very specific compositions like 75% nickel and 25% aluminum. That means in the unit cell there must be 3 atoms of nickel and 1 atom of aluminum. Similarly, I told you about the Au3Cu structure. This is also L12 structure, or you can have AuCu structure. This is an order tetragonal structure L21, or you can have copper zinc, which is a B2 structure. Okay. So, these are all different order structure, but if you see carefully they all has specific stoichiometry. Okay. So, what does it mean? That means that they are stable only at fixed compositions, but fortunately in metallurgy all these compounds can accommodate little bit of compositional change. Okay. We are lucky enough that this happens. They are not actually specifically compounds, but there are crystals which are specifically line compounds in the phase diagrams, but none of these are actually. Like if I talk about AuCu and AU3Cu, both of them has about 5 to 10% compositional differences accommodated from, suppose this is 75 25. So, you can actually start from 65 to about 85. Similarly, copper can be changed like that. So, copper zinc actually has a large compositional change. This is basically 50-50 percentage copper, 50% zinc, but in the center of the phase diagram of copper zinc you will see that this has a range of composition in which the B2 structure is stable. So, how do I show it in the free energy composition diagram? Suppose if I draw free energy composition diagrams of a compound which is as a very small range of solubility, then it will be like this. Okay. Suppose this has compositions of, let us suppose this is a composition of 25% aluminum. So, this is aluminum, this is nickel, sorry, this is nickel, that is aluminum, then otherwise it will be copper. So, this is 25%, but if you show clearly there is a range of compositions that is stable. This is where we can vary the aluminum concentrations or nickel concentration, by the way any of these are similar, and till we can actually retain the order structure. But there are there are phases, like I said to you, copper zinc. Okay, copper zinc has a large solubility around 50%. Suppose this is copper, this is zinc, and if I plot G and this is XZN, this is XL, XZN. So, you will find that it's basically this is 50-50, you will find that it is stable in a large composition range. So, we can actually get a shallow inverted parabola in the free energy composition diagram. But the most important characteristic of these compounds or these phases are that they actually, because they are stoichiometry, so they will be having free energies much lower than many cases than the solutions, specific solutions. It has been found. So, that is another advantage of forming these compounds, because they have a very order structures. So, therefore, the entropy contribution is low. Okay. And because of that, because atoms are in specific sites at in the lattice sites, so therefore, the configuration entropy is low. And what is important is the delta H, because delta H is very high here. Why? Because compound formations leads to a lot of energy release, and that is why the delta H is high, but delta S, the entropy change, is not very high. So, because of that, many cases they will sit much above the solutions lines. So, like if I have to draw it very clearly, then you can see here the FCC solutions which are nickel rich will be having much lower positions as compared to these. Now, if I want to find out the stability conditions for that, obviously, then what I should do? I should draw a tangent, common tangent between them, and that common tangent between them will tell you the solubility or the stability of these phases. Okay, as you can clearly see here, stability of these phases. Okay. So, that tells me that this is stable at 25%, but this is also stable between these, and this is stability of the compositions of the gamma solution. So, this is G gamma and this is G Ni3Al. Similarly, here, as you know, this is beta brass. So, obviously before that there will be alpha brass, very clear. Alpha brass has a composition large, it's basically also a stoichiometric compound, but it has a large solubility limits, and that is why this will be having, because this is stable from 0 to 40%, this will be like this. Then you can actually draw a common tangent and find out the stability change. This is 50 or this is probably 40% or something like that. So that is the way actually we can actually think about discussing about these structures. So difference between these and this diagram is that here, because of shallow natures of the free energy composition diagrams, it is same as the solutions what I discussed in the last class, but because of the stoichiometry of Ni3L is specifically defined and their composition cannot be varied very much. So that is why you have such a kind of construction presence. Remember, these all happens in the order compounds. Okay, these are all very specific things. Second important thing you should understand, these diagrams will also depend upon the order parameter. What is order parameter? It is very clear that in these diagrams I have shown you. In this diagram means here, what is that? Okay, let me go back. It is very clear that when in a big suppose material, large volume of material, if specifically in all the crystals, the atoms of Ni goes to the phase center positions and atoms of aluminum goes to the coordinates positions, then we have complete ordering. That means all the sites which are to be occupied by nickel are occupied by them only. There is no change of occupations of nickel from their original sites to other sites, or and vice versa, all the sites which are to be occupied by the aluminum are occupied. So that means its order parameter is equal to 1, then we define. But in reality it is not the case. Reality you will find there will be changeover. Some sites will be occupied, some specific sites, suppose for nickel, like here, if this atom, this side is not occupied by nickel but occupied by aluminum, then we call anti-side defects, but this will lead to reduction of the order parameter, and reduction of the order parameters is affected, will be affected in the free energy composition diagram, because the free energy you will change. Why? Because the moment you will have anti-sides, entropy will change, because you are then having little more randomness than a perfect order state. In a perfect order state it is completely randomless, but the moment you bring in these anti-side defects or some voids, suppose some nickel positions are not occupied by aluminum or nickel atoms, this remains a void, then what will happen? Entropy of that system will be much higher than a completely order structures. The moment you change the entropies, the free energy curve's position will change, and the moment free energy curve position will change, the stability will change. This can be seen easily. Suppose if I have this curve, okay, let me just little bit redraw it and tell you how it can happen. Suppose this curve goes down little bit. Suppose instead of this, let me draw with some other color. Okay, this is red color chalk. Suppose if the entropy increases and this goes down, free energy is still lower. Okay. Now what will happen? The common tangent will be little bit changed. So you see here the stability. Earlier stability was here, somewhere there, stability compositions, and this one although does not change much, but the composition stability is stable composition for the gamma phase, which is FCC solutions of nickel, has been decreased. So rather the range in which gamma plus Ni3Al is stable has increased. So that is what happened in natural aspects. Naturally these are the situations are observed, naturally these situations are very observed, because nickel aluminum has been studied extensively in the literature. So by changing the order parameter, basically we can do that. How do we define the order parameters? Order parameters are defined like this. It is basically S is basically equal to PAB minus PAB random or something. Let me just check. Random, yes, random minus PAB minus PAB. What is that? Complete order? No, this is maximum value minus random. Let me explain it. This PAB at the top in the numerator, the first one tells you the probability that all the sites, how many sites are occupied by A or B atoms, minus if it is completely random structure, then obviously there is no specificity of the occupations of the atoms in the lattice sites, divided by if it is fully order structure. Suppose the denominator where is suppose PAB max means it is a fully order structure, then what will happen? Every atom is sitting at the specific positions minus random structure. So, this value is much higher than this value. So, that tells you the order parameter. It can be actually changed over to the compositions of the unit cells, the composition of the lattices, we can change over that. That will, those are the specific things we will discuss later. So, in a very specific way, I like to tell us that the ordered crystal structures are, or solution structures are, or whatever compounds, they are actually compound most of the cases, some of the cases they are actually like copper zinc, these are solutions. We have a large range of solubility of zinc and copper in beta and alpha phases, or even gamma phases also in the copper zinc phase diagrams. You have a little slightly different way of drawing these free energy composition diagrams, and these diagrams will allow us to find out which phase is stable at what compositions at a particular temperature. Fine. So, in the next class we will simply go ahead and discuss about some of the aspects of equilibrium in heterogeneous systems. Although we have discussed few of these stuff, but specifically we will go into details. As you see in the books, if you go back to the books, it tells you how we can actually get these free energy composition diagrams for different systems, and that is what is very important. To understand that, you need to have a little bit idea about the phase diagrams, because I will be drawing phase diagrams and show you the free energy composition corresponding free energy composition diagrams at different temperatures, to show you how these free energy composition diagrams are important in terms of obtaining the phase stability. We will do that in the next class. So, hopefully you will be able to catch it up. Thank you.